Okay, let's look at this next exercise. It's very wordy and a little intimidating, admittedly, at first. But if we look at this, actually, they're giving us all the information for both the first derivative test and the concavity test. Okay, because here's some information about f prime. Here's some information about f double prime. So this is a nice sort of interesting way to pose a question where I'm testing you on your ability to understand the first derivative test and the concavity test without actually having to force you to take derivatives. Okay, so it's a good question. And so what let's realize is in this first derivative test here, we could see that the interval gets broken up for where the derivative is undefined here at 1, and then the derivative is 0 at 5. So I have these two critical values at 1 and at 5, and that's key to recognize. So these are my critical values. And it's breaking up the interval. So if I look at values between negative infinity and 1, values between 1 and 5, and values between 5 and infinity. And if I try to evaluate what's happening to the first derivative here on this entire interval, no matter what test point I pick, the first derivative, f prime, is positive. See, all these values are positive. So that's telling me that my original function, f, is increasing in this interval. Right? So you see how I'm filling out the table just from the graph. Now if I pick any test value between 1 and 5, any place in here, f prime is going to be negative. And that's telling me that f is going to be decreasing there. And then finally, any test point after 5, that's going to give me a positive derivative, right? My derivative is above the x-axis. My derivative is positive. So that's telling me the original function is increasing. Okay? So using the first derivative test, I'm going from increasing to decreasing and then increasing again. And so it looks temporarily like I might have a local max, but remember that if we look at the information, f of 1 is undefined, just like the derivative is undefined here. So this isn't a local max because x is not equal to 1, so it's not in the domain. But I do have a local minimum as I go from decreasing to increasing. So I have a local minimum at 5 comma something. How do I find that something? I go back into the original function and look to see if they tell me any information about that. Oh, they do. They tell me f of 5 is negative 3. So I found that I have a local minimum at 5, negative 3. Now we continue with the second derivative and noticing where the second derivative is 0 or undefined. So the second derivative is undefined again at 1, which is not at all surprising, right? If the original function is undefined, certainly its first derivative is going to be undefined there, and therefore its second derivative is going to be undefined. But we also see that the second derivative is 0 at 7. So this means that our domain is broken up into 3 intervals based on these two places where the second derivative are undefined and 0. So we're going to again think about our table, our concavity test. So we're going to test values between negative infinity to 1, 1 to 7, and then from 7 to infinity. And we're going to look at what's happening for test values for the second derivative in these intervals. So if I pick any value between negative infinity to 1, the second derivative is going to be positive, which tells me my graph is going to be concave up. If I pick anything between 1 and 7, still positive, right? This graph is above the x-axis, so that's still positive and still concave up. And then finally, if I pick anything after 7, I know it's going to be a negative result, so that's telling me concave down. So I see that I have an inflection point, a change in concavity at 7 comma something. And so to find that something, I go back into the original paragraph and I see that 7 comma negative 2. Okay, now we're asked to sketch the graph of f of x once we have the information, right? So we have a local minimum, we have an inflection point, we want to sketch all this information. So I'm going to clear some space. Okay, so I've got my local minimum here, 5, negative 3, and my inflection point, 7, comma 2. I also know that the function is undefined at 1, so we can go ahead and put a vertical asymptote in there. And so what we need to do now is, I know I've erased it, but you hopefully have information about the first derivative test and the concavity test. We want to put this all together. And so what happens is, up until the point of 1, for this entire interval, I've got, by the first derivative test, the function is increasing. Hold on. Okay. Sorry, I had a little technical glitch there with things moving around. Okay, so it's increasing and it's also concave up on that interval. So I'm ready to sketch in something that looks increasing and concave up, right? But I want to be a little bit careful because they gave me a little bit more information than usual, which is that I have some information about end behavior and about asymptotes. So, and I guess these right here are telling me about my those are my limits, left-sided and right-sided limits for 1. So those are those infinite limits as I approach my vertical asymptote. So I'll use those there. But here I'm getting information about, these are my infinite limits about the end behavior. So as x goes to infinity, as x goes to negative infinity, the function is approaching a horizontal asymptote down at y equals -1. So remember that a horizontal asymptote can be crossed, but it's telling us about the end behavior. So if I'm going to sketch in a piece that looks like this, I'm going to do so based on my asymptotes. So I'm going to have something like this. Okay, and again, here's the fact where I'm seeing that as x approaches 1 from the right, this function is approaching infinity. Okay, when I move now to the next interval, which would be between my vertical asymptote and my value at 5 here, so this is at my local min, the first derivative test tells me that the function is decreasing on this entire interval, right? And it's also, this the concavity test is telling me I'm still concave up. So I want to draw a piece that's sort of decreasing concave up, so something kind of like this. But again, I want to look for one other fact here, which is that at 2, the function is 0. So in fact, it's probably even a good idea for us. I probably should have, let's see, f of 0 is 2, so I didn't even draw that one in. So this is up at a height of 2. I didn't draw that very carefully. Okay, use that fact. F of 2 is 0, use that fact. F of -1 is 0. Okay, I didn't use that fact, and that was a little bit careless of me. So this x-intercept is back at -1. Okay, so I should have actually plotted all of the points that were given in addition to the local minimum and the inflection point. So if I were to redo this video, which I don't want to, that's what I would do. Okay, so the function is going to be coming down from positive infinity in a concave up way, right? So this whole time I'm supposed to be increasing. Gosh, this pen is not helping me out here. So I am decreasing concave up on this entire interval. On the next piece, I am now going to be increasing, but still concave up. So increasing concave up to my inflection point. So here's my local min. This one, remember, was my inflection point. From here, I'm going to be still increasing, but concave down. So I'm concave down and heading off towards my horizontal asymptote down at -1. All right, not my most clear video. I apologize for that, but hopefully you get the idea how you can take information from a graph or a table or something. So even if you don't have an actual equation for a function, you can still work through the first derivative test and the concavity test to sketch functions or find max, mins, and inflection points.